Assalamualaikum warahmatullahi wabarakatuh. Nama saya Nurnichani Zamita Zulkafli. Nombor matrik saya S711165. So, I will discuss about the introduction of cephalotaxin. So, let's go into the introduction of cephalotaxin. Natural products from plant have long played a key role in medicines. Among these, alkaloids, nitrogen-containing compounds are known for their powerful pharmacological effects. One such alkaloid is cephalotaxin, a secondary metabolite found in the Japanese plum yew, which is Cephalotaxis harringtonia. Cephalotaxin has a complex tetracyclic structure and serves as a chemical foundation for more effective semi-synthetic drugs such as homoharringtonin HHT. While cephalotaxin itself is not widely used in clinics, its derivative HHT is gaining attention as an alternative treatment for chronic myeloid leukemia (CML), especially for patients resistant to standard tyrosine kinase inhibitors. Next, let's move into the application of cephalotaxin. Cephalotaxin is an alkaloid from Cephalotaxis harringtonia, which is a Japanese plum yew, native to Japan and Korea. It has limited direct pharmaceutical use, but it is the precursor to important anti-cancer derivative. Firstly, pharmaceutical significance of derivative, which is the homoharringtonin, which is HHT. It is used for chronic myeloid leukemia, especially in patients resistant to tyrosine kinase and inhibitors. It inhibits protein synthesis during translation elongation and binds to the ribosome site, preventing amino acid tRNAN3, and it leads to apoptosis, particularly in BCR and ABL mutated leukemia cell. Secondly, anti-cancer research potential. Cephalotaxin and its derivatives show cytotoxicity against the several cancers, which is leukemia, lung cancer, breast cancer, liver cancer. SAR, which is structure activity relationship, studies show the 3-hydroxyl ester substitution is critical for activity as seen in HHT. Thirdly, potential for drug development. Researchers are modifying cephalotaxin to improve selectivity, potency, solubility, pharmacokinetics. It continues to serve as a valuable scaffold for designing new anti-cancer agents. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. Nama saya Nur Eva Rizwani binti Abdullah. Nombor matrik saya S7149. So, I will discuss about chemical structure of cephalotaxin. So, as we can see from the picture that I have given, which is the structure of cephalotaxin, it is a complex natural alkaloid with the molecular formula of C18H21NO4. It has a molecular weight of approximately 315.4 gram per mole. The structure consists of 4 fused rings forming a rigid polycyclic skeleton. It also contains a methoxy group, a hydroxy group at 3 positions, and an ether bridge as part of its dioxazine ring. The stereochemistry of this structure, it has several stereocenters, notably at position 2, 3, and 6 on in the S configuration in the natural enantiomer. The nitrogen atom is part of quaternary center, contributing to the rigidity and unique three-dimensional shape of the molecule. Class of compound for cephalotaxin. Cephalotaxin belongs to the class of alkaloids, specifically the cephalotaxin type alkaloids, which are isolate from blends of the genus Cephalotaxis, which is family Cephalotaxaceae. It is classified as an alkaloid because it has nitrogen within a complex polycyclic heterocyclic structure, typically of alkaloids. These alkaloids are characterized by their unique tetracyclic skeleton and are distinct from other alkaloid families due to their structural complexity and biosynthetic origin. Cephalotaxin is isolated from cephalotaxis species such as Cephalotaxis harringtonia. Some related compounds is omacetaxin, known as Homo harringtoni. It is a semi-synthetic derivative used clinically as protein synthesis inhibitor in leukemia therapy, sharing the cephalotaxin core. Not only that, cephalotaxin type alkaloids are subdivided based on oxygenation pattern, with cephalotaxin itself belonging to the C11 non-oxygenate class of these alkaloids. The structural features nitrogen heterocycle, multiple fused rings, and stereochemistry define its classification as an alkaloid rather than other compound classes like terpenes or flavonoids.
Assalamualaikum and hi to doctor. My name is Nora Awatif Atira binti Muhammad Yusof and my metric number is S71000. And for today, I would like to present for the title of my written assignment, which is cephalotaxin, and my part is building block. So, before I go through to the building block, I want to explain a little bit what is cephalotaxin. So, what is cephalotaxin? Cephalotaxin is natural alkaloid from Cephalotaxis species. It possesses for pentacyclic structure and is also known for anti-leukemic properties. Cephalotaxin also complex for stereochemistry and ring system. So, let's go through to another part, which is key building blocks. So, for the key building block, cephalotaxin synthesis typically break down into molecular unit or building block, often targeting three parts, which is first, benzodiazepine core. For the benzodiazepine core, it consists of 7-member nitrogen-containing ring fused to a benzene. For the second, it's also constructed to via intramolecular cyclization or rearrangement strategies. Okay, for the second part, we have hydroxylated side chain. For the hydroxylated side chain, it forms part of the key stereocenter at C3 and C4 carbon position. It's also introduced via enolic chemistry or isometric synthesis. Okay, for the last part, which is third part, we have the spirocyclic or tetrahydrofuran ring. For the this part, this oxygen-containing ring is crucial for biological activity. It often introduced through cycloaddition or nucleophilic ring closure. Okay, let's move to the another part, which is synthetic highlight. For the synthetic highlight, the stereocenter formation is critical, especially at C3 and C4 carbon. It used for Friedel-Crafts isolation, peptide Spengler or Azacope rearrangement, and palladium catalyzed acylic alkylation. That's all for the building block structure. Okay, for this part, I will explain about the biosynthesis of cephalotaxin, which is Homo erythritol-like pathway. For the first, I will explain first about the pathway hypothesis. For the pathway hypothesis, it's modeled after Homo erythritol alkaloid biosynthesis. It's considered the favored biosynthetic route for cephalotaxin. For the starting material, we use amino acid, which is phenylalanine or tyrosine. For the key conversion, phenylalanine will turn to the phenylacetaldehyde, while tyrosine will turn to dopamine via the decarboxylation or hydroxylation. For the key reaction, peptide Spengler reaction form 1-phenyl tetrahydroisoquinoline, which is distinctive due to phenylethyl, not to the benzyl side chain. Okay, for the ring closure process, oxidation form a dione intermediate.
which is intramolecular cyclization, yields tetracyclide cephalotaxin scaffold. For the evidence from isotopic labeling, I have provided the image, which is we will saw the C of C6, C7 and C8 is from C3, C2 and C1 of phenylalanine, and C10, C11 will from C2 and C3 of tyrosine. That's all for biosynthesis of homoerythritol pathway. Thank you.
Next, we will proceed to a laboratory synthesis of cephalotaxin. As we all know, cephalotaxin is a complex alkaloid with a tetracyclic structure and several carbon centers. Its synthesis is challenging due to structural complexity and stereochemistry. So, the synthetic strategy that we propose is retrosynthetic analysis, which is it breaks the molecule into simpler building blocks. It also have aromatic aldehydes, phenols, beta ketoesters, and nitrogen-containing heterocycles. Next, the key reaction includes Michael addition and aldehyde condensation for CC bond formation, intramolecular cyclization to form polycyclic structures, reductive amination to introduce nitrogen atoms, and asymmetric catalysis to control the stereochemistry. In addition, M.E. Kuhni in 1990s synthesized cephalotaxin via over 20 steps, which is he used intramolecular alkylation and asymmetric catalyst. It also produced a molecule identical to natural cephalotaxin. The significance is synthesis is labor intensive due to stereochemical and structural challenges. A major achievement in organic synthesis, and the last one is aids in the development of semi-synthetic drugs, especially in cancer therapy.